So to start off, you just need to draw a simple best fit curve through all the data points. Just what you had to do is you had to make sure that the line connected all the data points, because that's what a best fit line needs to do in this case. And then for the second part, it says you need to reason a reasonable interpolation of the value when m is equal to 250. So just use your best fit curve and then find the point. And on the example graph from the AP problem, it's supposed to be x, when the mass is 250 kilograms, the distance is 33 meters. And then, alright, for the next part, you can just use kinematics to find the time. Because for the free fall, you can use y equals 1/2 gt squared, because the catapult is just going to go up and down, and you can just use the free fall. From the top, it's just going to fall down to this point, and you can just use free fall to find the time. And so t is then equal to the square root of 2y over g, and then you plug and chug and you get t is equal to 1.75 seconds. Alright, and then for the next part, define the potential energy of the load, of both the load and the counterweight bucket and the projectile. So you need to use, for the value of the potential energy in the bucket, you need to use mgh, and then so that's equal to m is unknown, it's a variable, and then times gravitational constant, and then times the height, which is 3 meters, and so that's all equal to 29.4 m. And then the potential energy of the counterweight is equal to the projectile is equal to mgh, and that's equal to 10, since you know the weight and it's 10 kilograms, times 9.8 times 3, and that's equal to 294. And so the final potential energy is equal to those things added together, which is 29.4 m plus 294. Alright.
You need some toilet paper, Lawrence?
I do. B. Okay, so for the third part, you need to use conservation of energy. So U initial is equal to the potential energy final plus kinetic energy. So you get a point for stating conservation of energy. And then you need to find the final potential energy of the bucket load and the final potential energy of the projectile. So U final is equal to m 9.8 1. This is of the bucket load, I think. Yeah, this is the bucket load, and it's 1 meter above the ground, as it shows in the diagram. And then you add that to the potential energy of the projectile, which is 10 times 9.8 times 15, and then you get 9.8 m plus 1470. And then for having the final kinetic terms in the final, kinetic energy of both the bucket and the projectile, so you do k of the projectile is equal to, you use 1/2 mv squared. So 1/2 10 for because the projectile, you know, weighs 10 kilograms, times vx squared, and then kb is equal to 1/2 mvb squared.
Oh, watch out, Lawrence. Let me get.
What?
Okay, there we go.
Alright, and then the relationship between VB and VX is VB is equal to 1/6 of VX. Because if you look at the diagram, like the distance is 6 times that. If you look at like the ratio, it was like 12 to 2 or something. Yeah, that's why there's this ratio you can use. And then substituting into the conservation of energy equations above and solving for Vx. And so you do 29.4 m plus 294 is equal to 9.8 m plus 1470 plus 5Vx squared plus m over 72 Vx squared, and then you just solve, and then you get Vx is equal to 19.6 m minus 1176, and then all of that is over 5 plus m over m divided by 72, and yeah, and then for the next part, you can just use, to find the distance, you can just use x equals v xt, and then you can just substitute in Vx and the time which you already got from a previous part of the question. And so it's 1.75 times that answer in the last part, which is 19.6 m minus 1176 divided by 5 plus m over 72. And then for the final part, you have to use the equation from part C to predict x theoretical. And so x theoretical would be, you just plug in a value of m, and the value of m when it's equal to 300, and then you plug it down here, so plug in 300 there, and then you end up with 39.7 meters. And so this experimental value is less than the this theoretical value is less than the actual experimental value. And so you can offer any sort of, a bunch of like reasonable explanations. Like you can say that it's because of friction, and because of friction there was some energy converted into heat, or like there could be air resistance, or like some of the neglected masses, like they actually distorted the problem a bit. I think the easiest one to do would probably just be say that there was friction and energy lost due to heat, and that's it.
Lawrence likes men.